Hi guys, in this video we're going to talk about the expressivity of the neural network's architecture. Specifically, we're going to look at 0, 1, and 2 hidden layers. A lot of the information in this video is taken from this book by Christopher Bishop, Neural Network for Pattern Recognition. It's an old book, it's from the 90s, I think 95 or 96, but it has a lot of insight. Some parts are a little bit outdated maybe, but I highly recommend it. There's a lot of insight going through this book. I read about half of it and leafed through the rest. I gained a lot of insight from reading this book. So a little bit of terminology. So I'm using the number of hidden layers as my reference point. So 0 hidden layers means there's just inputs and outputs. 1 hidden layers mean that there's the inputs, they go to one processing layer, and then there's the outputs. And of course, we are talking here only about feed-forward neural networks. There are also other architectures like convolutional neural networks, recurrent neural networks, etc. Okay, but in the book, they call 0 hidden layer, for example, 1 layer network because there's 1 linear layer. Yeah, so the inputs, they go through 1 linear layer, and then there's the outputs. And other people might call 0 hidden layer 2 layers because there's the inputs and the outputs. So maybe it's 2. Yeah, so there's a little bit of mix of terminology, but I prefer to use the number of hidden layers as my reference point. So let's look at 0 hidden layers. If we look at regression, well, we basically have just input, they go through a linear layer without any activation, and we get an output. So it's basically linear regression. Yeah, this is what we get from this architecture. And so the structure that this architecture can capture is basically a hyperplane. Yeah, so if the input is only 1 dimension, then we at most can get a line. And like always, there is some bias term. Yeah, like always. I won't write it from now on, but there is a bias term. This is 1, and this is the b. Okay. And so if we only have 1 input, then we can get a line. If we have 2 inputs, we can get a plane. And in higher dimensions, we get hyperplanes. For classification, it's the same architecture. Yeah, we have some W and B here, some linear layer, but here we will add some activation function. Yeah, let's say a sigmoid. The sigmoid will make sure that we are getting numbers between 0 and 1. And so this is the output of this 0 hidden layer architecture. And now the decision boundary can be represented by a d-1 dimension hyperplane. So if we have 1 input, then basically there will be a point. Yeah, so some point that before it will be 0, and after it will be 1. Yeah, before it will be 1 class, and after it will be another class. And we are looking here at binary classification. If we have 2D, yeah, if our input is 2D, then we will have some line. Okay, so here you can see a visual of it. So the red and the green represents our maybe x1 and x2, and the blue represents the y hat. Okay, so we will have a line here in the xy plane. Yeah, if we project it only on the xy plane, we will have a line, and everything on one side of that line would be a 0. Yeah, here would be 1 class, and everything on the other side of that line would be a 1. Yeah. For multi-class, the architecture will have a linear layer, but this time instead of 1 output unit, there will be C output units. Yeah, so C is the number of classes. So suppose we have 3 classes and 2 inputs. This is how the architecture would look like. And then after that linear layer, we can either use individual sigmoids on each of the neurons here, and then just choose the largest value as our predicted class, or we can use a softmax. And both are equivalent, right? Because if the sigmoid of one value is bigger than the sigmoid of another value, it only happens if this value is bigger than this value, but this also only happens if the softmax of this value is bigger than the softmax of this value. And if this is the largest value, it will also be larger than all of the others. Yeah, so softmax and sigmoids are equivalent architectures. Okay, so here we will have a linear architecture, and then some activation function, which can either be a sigmoid or a softmax. And of course, the linear will make it that we will have some W1x here and some W2x here and some W3x here as the inputs. Yeah, these are the inputs before the activation, and then we do the activation on them and we get the results. Either plus a bias term or we include the bias already in the W's and the X's. And so the decision boundaries in this case partition the space into convex region. It's basically these lines and that partition the space. This, okay, there's a little bit of artifacts here, but it should be a straight line. Maybe we watch it on GeoGebra. Okay, so you can see this is how it looks like. This is one region basically outputted by the first neuron sigmoid. This is another region outputted by the second neuron. And you can see this is the line where they are the same. It should be linear, but there are some artifacts. Here, the purple is bigger and here the green is bigger. And finally, this is the third line. Here, the light blue is bigger. Okay, and this is how the decision boundaries look like. And we can actually also prove that the regions created by this architecture are convex. Yeah, so a convex region or a convex set means that for every 2 points in the set, let's say point x1 and point x2, all the points that are on the line that connects them are also in that region. Okay, so all the points, mathematically we write it like this. Alpha can be between 0 and 1. If alpha is 1, we are in this point, we are at x1. If alpha is 0, we are at this point. And as we move alpha from 0 to 1, or from 1 to 0, we are getting all these other points here. Okay. And so suppose that we have 2 points and they are in the same region. So what it means, and let's for the sake of simplicity assume that it's the first region. Yeah. So what it means that the output of the neuron, of the first neuron, is the largest, right? For x1, and it's also the largest for x2, right? So this neuron, let's call it y1 hat, is bigger both for x1 and both for x2. Yeah, and x1 is 1 point in this 2-dimensional plane, and x2 is another point in this 2-dimensional plane. Okay, so y1 is larger than any other yj, so from y2 and from y3. And so this can only happen if the inputs to that activation function is bigger than any other inputs. Here we said this is the input to y1, and y1 will only be bigger than y2 hat if w1x is bigger than w2x. Yeah, plot bias or swallow the bias into the w's and x. Okay, and the same goes to x2. So w1x2 will be bigger than all the other wx2. It will be bigger than w2x2, and it will be bigger than w3x2. Okay, so now let's look what happens for all the other points. So if we take w1 time any other point, yeah, and alpha can change from 0 to 1, any other point in that line that connects x1 and x2, and open it, we get this expression. So we know this is bigger than this because x1 is in class 1, and we know this is bigger than this because we know x2 is in class 1. And so this is a positive number. This is bigger than this. This is also a positive number. So we got this inequality. And now we can plug out wj and we get this. And so we see that for every point that we want on that line that connects x1 and x2, the linear term w1 times that point will be bigger, yeah, than the linear term of any other wj, which means that the y hat will be bigger for this point than any other y hat. So y hat 1 will be bigger for this than y hat 2 and y hat 3, which means that this point will also be in the same region. Yeah, so we proved that this is convex. Okay, but as you can see, this has a very limited expressibility because, so for example, the XOR function, which is a very simple circuit logic function, which looks like this. It has one, and actually what I graphed here is the opposite XOR, yeah, but it doesn't matter. Okay, so imagine that these are zeros and these are ones. Okay, so the XOR, the exclusive OR, gives 1 if only one of the two is 1, but it gives 0 if both are 0 and both are 1. this cannot be modeled using any linear architecture. Yeah, no linear line that you can pass can correctly classify these 4 points. Yeah, if you say, okay, everything here is 1, you are mistaken on this point, right? Because this is 0. And no matter which linear line you will put, you won't be able to correctly classify all 4 points. And this is a very simple case where we take, for example, that the x's only get binary values. But even if the x's get any continuous values, this is a very limiting architecture. We cannot, it has a very limiting expressibility. So for example, if we take a lot of points and then label them randomly, and these different sets are called dichotomies, the percentage of dichotomies that can be correctly labeled, it goes down really fast as the number of points become larger. So for example, here in this 2D space, if I take 3 points, yeah, that are in general position, meaning they are not on some degenerate form. So if they are all in the same line, I have a problem. But in general position, meaning that they are not in some subspace of that big space. So if I take 3 points, no matter how I want to label them, if I want to give these ones and this 0, it doesn't matter. I can find a linear decision boundary that correctly classifies it. But if I take 6 points and I randomly classify them, then it turns out about half of the time I will be able to correctly classify them, and about half of the time it will be impossible to correctly classify all of the points. And if I take even more points, then the percentage goes to 0. And here's a graph from the book that shows it. I'm looking at the ratio of the number of points and the dimension of the input space plus 1. So in our case, we had that the input space was 2, and so plus 1 is 3. So if we have 3 divided by 3, we can see we are in 1, and the ratio of correct classification is 1. So we can correctly classify all 3 points. If n goes to 6, the ratio goes to 2, and we can correctly classify only half of the points. And as it goes bigger and bigger, we see that it goes to 0. And as d gets larger, the fall becomes much more steeper. Okay, so this was 0 layers, very limiting. Let's look at 1 layer. So with 1 hidden layer, the intuition is that you can just combine different kinds of linear function. So let's take an example. Suppose x is again 2-dimension. The true y's are 0, 1, so we have a binary classification. We have 1 hidden layer with 3 neurons, a sigmoid activation function, and another linear layer, and then the outputs also have a sigmoid activation function. And suppose this is how the points are classified. So we have this outer ring of orange points that, let's say, are class 0, and we have this inner circle of blue points that are class 1. And so each neuron in this middle layer, in this hidden layer, can create a separation line, which is linear. And if we now stack these up together, we can create shapes. So for example, suppose in the final output, we have negative bias of minus 0.1. So unless otherwise specified, everything is orange. And then we say, okay, we draw a line here, and we say everything here gets a plus 3.7. So basically all these points to this side of the line should be blue. But then we correct it a bit more and we say, you know what, all the points here, we subtract 3.7. So they are back to the bias of minus 0.1. So they are again orange. And then we say again, you know what, also all the points here should also get minus 3.8. So they are again orange. And notice that the lines here, the shape here is not a perfect triangle. And this is because of the sigmoid. So the sigmoid has this, it doesn't jump immediately from 0 to 1. It has some curving. And in this curving is what allows these soft edges to form. So because of the sigmoids, instead of having a triangle here, we are getting this soft thing here, and also this soft thing here, and this soft thing here. Yeah. So this is kind of how you create a region with one hidden layer. And just as an exercise, you saw before we had this XOR problem, then maybe you can try to create a neural network architecture which can correctly classify XOR function. And a few hints, maybe it will be easier if you use a threshold activation. So a threshold activation is just below 0, it gets 0. After 0, it gets 1. It's a step function, or I think it's also called the Heaviside function. And another hint is that this architecture is enough. You don't need anything more than this. Okay, so try to solve it and maybe post your answer in the comment section. And so the question is, how expressive is a neural network with just one hidden layer? So we see here it can create these convex regions. Is that all it can do? Well, no, it can do much more, but let's get back to it later. Let's first consider the case of two hidden layers. So what is two hidden layers? Well, we have the inputs, we have one hidden layer, we have another hidden layer, and then we have the outputs. And it turns out that with two hidden layers, you can approximate any function, given that you have enough units. And so it can create any shape that you want in the input space. And let's look at a short hand-wavy proof. So the basic idea is that any function can be approximated by a superposition of bump function. Let's see it in 1D space. Yeah. So for example, suppose I have this function, I can just create these bump function, yeah, these bars to approximate it. And then I can just put them together and make a linear combination of them and recreate this complicated function. But this is true not only for 1D, it's true for any dimension. So let's look at it at 2 dimension. We use sigmoids in the first and second layer. And so one sigmoid looks like this, right? We already saw that if our input space is 2-dimensional, then one sigmoid would look like this. If we take 2 sigmoids in opposite direction, we can create this ridge. And maybe I show you this here. So I have one sigmoid here. Okay, this is how it looks like. And then I have another sigmoid, which is just a bit shifted. And now I take the second sigmoid minus the first sigmoid, and I get this ridge object here. Okay, so we can connect sigmoids to create this ridge. And now we can put 2 ridges together in opposite direction to create this function over here that will have 4 ridges, but a bump on top of it. Okay, so I created another ridge that has an opposite orientation. And now if I put them together, I'm getting this function that has a maximum. Yeah, there's like 4 ridges going out of it, but one maximum. So I have this maximum function, yeah, this 2 ridges together. And then what I can do, I can pass it through another sigmoid, and this will soften the ridges and make the peak more distinct. And I can play with this to create this, what is kind of a bump function, yeah? So now the ridges are very, very low and the bump is very high, and I can play with it to create different bumps and put them together to create the function that I want. Okay, so this is what this image shows. And this is how the network architecture will be. We will basically have, in this case where it's 2D, we will have 4 neurons, yeah, in the first layer. This is the first layer. This is the second layer. So 1 neuron creates a sigmoid, 2 neurons create a ridge, 4 neurons create a bump function. Yeah, so all of these go into here with linear combination to create a bump function. Then we pass it through another sigmoid. This gives us this bump function. And then we combine all the different bump function together to create whatever function we want. And this generalizes to also R1, of course, but also to R3. And if I'm not mistaken, you would need 2 to the power of d neurons per bump on the first hidden layer. So here we had 2, so 2 to the power of 2 is 4. The book says 2 times d, but I think it's a typo. Okay, so now let's get back to one hidden layer. And it turns out that even with just one hidden layer, you can approximate any function. And this is often called the universal approximation theorem. And there's a lot of researchers who were involved in this. One of them is called Cybenko, and he had a work published in 1989. So let's look at a simplified proof using one-dimensional x. Yeah, so we have one-dimensional x, one-dimensional y, so a very simple function. And again, the basic intuition is that every function can be approximated by a superposition of bump function. So any two neurons in the one hidden layer joined together can create a bump. And the output layer can simply scale those bumps and add or subtract them together. So for example, here, suppose that this is 3 and this is 4 and that this is 10, then, and suppose that our activation function of the first layer is a threshold function, so not a sigmoid but a threshold. Any sigmoid can be turned essentially into a threshold if you make the weights big enough. Yeah, so it will become, from this, you can make it more and more tight until it becomes something like this. Yeah. But for the sake of simplicity, let's consider that it's a threshold. We can take one function to be x minus 3 and then the activation, another neuron to be x minus 4 and then the activation, and then the output will just take 10 times the first minus 10 times the second. Yeah, so we have, this is our input, it's just one value, and then there's two neurons. Okay, both of them have the weights of 1. In one of them, the bias is minus 3. In the other one, the bias is minus 4. So here we have x minus 3 as the input. Here we have x minus 4. Then we take the threshold function on both of them. And then the y will just take 10 times this and minus 10 times this. And this will create this bump function over here. Okay. And then there are other neurons that will create the other bump function, and we will just add them together. So for example, if I have my input is 3.5, only these two inputs will be non-zero, the rest will be 0, and so I don't care about them. And this is how we can create this function, our function here, y, using only one hidden layer. Okay, so we have one input, one output, and one hidden layer. But in this case, we need a lot of neurons to create this function. And this was in 1 dimension. You can also do it in 2 dimensions, but this requires a lot more math. So for example, if I understand correctly what he says in his book, then every function of 2 inputs can also be transformed into functions, sums of functions of 1 input, using Fourier series or using Fourier decomposition. So this is the Fourier series of a 2-dimensional function. Notice there's a lot of trigonometric function, cosinus and sinus, and they are multiplied. But then we can use trigonometric identities, which I'm giving here, to turn this into, instead of multiplication, to sums of cosines and sines. And so this can be expressed as some form of coefficients times cosinus of these linear things over here. But now, so every cosine function or every sinus function can also be approximated using a bump function. So for the first cosine, we might need, I don't know, a bazillion number of neurons just to approximate the first cosine, and then another million neurons just to approximate the second cosine, etc., etc. And then the output layers just approximate these alphas and betas coefficients and sum up these cosine and sinus. Yeah. So the architecture is we have, in this case, 2 inputs, and then we have to create a whole tons of neurons just to approximate using bump functions the first cosine. Yeah. So this is just for the first cosine, but then we have to do the same for the second cosine, do the same for the sinus, etc., etc. So you will need a lot of neurons in this one hidden layer just to create all these functions, and then you combine them together to the output layer. Yeah. So I hope I got the math right. I'm not an expert. It could be that I have some mistakes, but in any case, the main point is that there are theorems that show that not even just for 1D, but for 2D, 3D, etc., you can use only one hidden layer and you can approximate whatever function you want. Okay, so here's the conundrum or the mystery. If theoretically we only need one hidden layer, and it might be that we need it to be very long, but still, why do we use more? So first of all, as you could see, even for two-dimension case, with one hidden layer, it seems that we need a lot of neurons to approximate the cosine and sinus terms, whereas with two hidden layers, we only needed 4 neurons per bump, and then we could just superpose these bumps together. And this is just if we want to use this bump structure, but it could be that the structure is much more simple, and we actually don't need so many bumps together. And then it could be that the first and second layer have much less neurons. And so in general, it seems like deeper layers allow for more efficient representations. Also, these universal approximation theorems, they only say that it's theoretically possible to represent any function using just one hidden layer, but in practice, it might not be feasible to get the correct weights, the correct coefficients of this network using optimization. It could be that it's just not feasible practically. And so Bishop's book in 1996 said that one possibility is that by using extra layers, we might find more efficient approximation in the sense of achieving the same level of accuracy with fewer weights and biases. In total, very little is currently known about this issue. This was 1995, 1996. There has been some work trying to figure out more and prove more. I don't think there's been a lot of work. One of my professors in the course I took mentioned Yarotsky in 2017, and he had a work that showed that deeper networks work better on smooth functions than shallow networks. So basically, there are certain conditions that even theoretically, it's better to go deeper than to stay shallow in your neural network architectures. And if you know some other works that I don't know, please leave them in the comment sections. And also, I want to go again over this idea of compound structure. So basically, if you add more layers, you can kind of think of it as if everything before that final layer just tries to find a simple space. It's basically sort of feature engineering. Yeah, so it's basically moving from X to some phi of X, some other space of X, some other features of X. And then in the final layer, well, it's like you have a 0 hidden layer network, and all it can do is find a linear separator. And so in that final layer, it has to be that these features are linearly separable. So basically, you could say that having deeper layers moves you from complex spaces to more and more simplified spaces where the decision boundaries become more and more simple. So for example, it could be, if we go back to this image example, that just looking at edges and having a lot of different edges together, it's really hard for us to determine if it's a house or a car. But then moving from edges to simple shapes like circles and squares, well, it's still hard. But then if we move from squares and circles to more complex shapes like houses and cars, then in that space, it could be that houses are in a certain place and cars are in another place. And then we can pass a linear separator in that space to distinguish between them. So to sum up, 0 hidden layer only allows you to have linear separability. So basically some hyperplanes, a line, a plane, a hyperplane, etc. One hidden layer theoretically can express everything already, practically not, because you would need an insane amount of neurons. 2 hidden layers and more already allows you for much more efficient expressivity. And so according to the problem that you have and its complexity, you might need to use more and more layers. And I can recommend you playing a bit with it using this playground that TensorFlow has. And let's move to it to see it. Okay, so it looks like this. And this is the problem that I used in the video. And we can reset it and let it work. You can choose the activation functions. You can choose the number of hidden layers, the number of neurons. And you can see how the training loss and also something called the test loss, which I will discuss in a future video, converge. And you can stop it and see the final result. You can do other problems. You can play around with it. Here's another problem. And here I used 4 neurons, and you can see how it works. So I really recommend you playing a bit with it to kind of get the feeling of how the architecture basically limits or defines the amount of expressibility that the neural network has. So this is all for this video. I hope you enjoy it and see you in the next one.